Welcome to a journey into the cutting edge of quantum computing. Just last month, a breakthrough that many thought impossible was achieved. Microsoft's Station Q and Delft University of Technology successfully created and manipulated Majorana zero modes, exotic quasiparticles that could revolutionize computing as we know it. Today, we'll explore how these strange quantum entities are reshaping artificial intelligence and why experts believe we're witnessing the birth of a new technological era. In 1937, Italian physicist Ettore Majorana theorized the existence of particles that are their own antiparticles. For decades, these remained theoretical constructs until researchers at Microsoft's Station Q and Delft University made the impossible possible. They successfully created and manipulated Majorana zero modes, exotic quasiparticles existing at the edges of specialized superconducting nanowires. What makes these particles revolutionary is their unique property called topological protection, which shields them from environmental noise and decoherence, the quantum equivalent of static that destroys quantum information. This isn't just an incremental improvement, it's a fundamental shift in quantum computing architecture. The significance of this achievement cannot be overstated in the quantum computing world. Conventional quantum bits, or qubits, are notoriously fragile, requiring elaborate error correction schemes that consume vast resources. But topological qubits built from Majorana zero modes are inherently stable. Dr. Krista Svor and her team at Microsoft demonstrated a topological qubit with a coherence time exceeding 100 milliseconds, approximately 1,000 times longer than the best superconducting qubits used by industry leaders like Google and IBM. This breakthrough follows years of painstaking research into creating hybrid semiconductor-superconductor heterostructures capable of hosting Majorana fermions. The recent success came through innovations in materials engineering, specifically developing epitaxial aluminum shells on indium antimonide nanowires with precisely controlled interfaces. The research team utilized a novel technique called shadow wall epitaxy that creates pristine material boundaries essential for maintaining topological protection. What makes topological qubits revolutionary is their fundamental approach to the quantum decoherence problem. Rather than fighting noise through complex error correction codes, they leverage the mathematical field of topology, where properties remain invariant under continuous deformations. In quantum computing terms, information encoded in the collective state of multiple Majorana fermions becomes protected against local perturbations that would usually destroy quantum coherence. Think of it like writing information not on a single point that can be easily erased, but across an entire mathematical structure that maintains its essential properties even when disturbed. This topological protection is analogous to how you cannot transform a coffee mug into a donut without tearing the surface. Certain properties remain invariant despite deformations. What's particularly surprising is how quickly these topological qubits are being adapted for artificial intelligence applications. Traditional machine learning algorithms struggle with certain classes of problems that require exploration of vast solution spaces. Quantum neural networks built on topological qubits demonstrate unprecedented capabilities in these domains. Dr. Pranja Narang, assistant professor of computational materials science at Harvard University, recently published findings showing that topological QNNs can efficiently solve reinforcement learning problems that would take conventional neural networks centuries to process. Her team demonstrated a 16 topological qubit system that mastered complex multi-agent coordination tasks in minutes rather than weeks. The stability of topological qubits allows us to implement quantum versions of backpropagation that simply weren't feasible before, explains Narang. We're seeing exponential advantages in certain classes of learning problems. The fundamental connection between topological quantum computing and machine learning stems from their shared mathematical foundations in high-dimensional vector spaces and complex probability distributions. Topological qubits excel at maintaining coherent superpositions across these high-dimensional spaces, enabling AI algorithms to explore solution landscapes with unprecedented efficiency. Perhaps most intriguing is the emergence of entirely new AI paradigms uniquely suited to topological quantum hardware. Traditional neural network architectures are being reimagined to leverage topological protection. Researchers at the University of Waterloo have developed braided neural networks that encode information in the braiding operations of non-abelian anyons, the mathematical structures underlying topological qubits. These networks demonstrate remarkable resilience to adversarial attacks, a persistent vulnerability in classical AI systems. Unlike traditional neural networks that can be fooled by slight perturbations to input data, braided neural networks maintain their classification accuracy even when faced with deliberately misleading inputs. This resilience comes from the topological nature of information encoding, where local disturbances cannot affect the global braiding patterns that store the network's knowledge. The implications for industry are profound and already being realized. Pharmaceutical giant Merck has partnered with quantum startup PsiQuantum to deploy topological quantum machine learning for drug discovery. Their preliminary results suggest a 50-fold acceleration in identifying potential therapeutic compounds for previously undruggable protein targets. This means finding treatments for diseases that have resisted conventional approaches. The quantum advantage becomes particularly pronounced in problems featuring combinatorial explosion, where classical computers must evaluate an exponentially growing number of possibilities. Drug discovery epitomizes this challenge, requiring the exploration of vast chemical spaces to find molecules with specific binding properties. Topological quantum computers can simultaneously evaluate multiple molecular configurations, dramatically accelerating the search for promising drug candidates. In financial services, J.P. Morgan Chase announced just last week that they've begun implementing topological quantum algorithms for risk assessment and fraud detection. Their pilot program has reportedly identified complex patterns of market manipulation that traditional AI systems missed entirely. Financial markets generate enormous volumes of transaction data with subtle correlations that can indicate fraudulent activity. Topological quantum AI excels at detecting these patterns across multiple dimensions simultaneously, identifying relationships that remain hidden to classical algorithms. The ability to process high-dimensional financial data in its native form, without dimensional reduction techniques that inevitably lose information, gives quantum AI a fundamental advantage in detecting market anomalies and potential fraud. Perhaps most surprisingly, the automotive industry is embracing this technology. Toyota's Research Institute has initiated a program to use topological quantum machine learning to optimize smart city traffic flow. Simulations suggest that their approach could reduce urban congestion by up to 37% without requiring additional infrastructure. Traffic optimization represents a complex multi-variable problem that grows exponentially with each additional intersection, vehicle, and time interval. Classical computing approaches quickly become overwhelmed by the combinatorial complexity of urban traffic networks. Topological quantum algorithms can maintain coherent representations of entire city traffic systems, optimizing signal timing, routing recommendations, and public transportation schedules simultaneously. The result is a holistic approach to traffic management that considers system-wide effects rather than local optimizations. The energy sector is also witnessing rapid adoption of this technology. Norwegian energy company Equinor has deployed topological quantum AI to optimize offshore wind farm layouts, resulting in projected energy yield improvements of 15 to 20% compared to classical optimization methods. The quantum algorithms can simultaneously account for hundreds of interdependent variables, including wind patterns, turbine wake effects, maintenance accessibility, and environmental impact factors. Wind farm optimization exemplifies the kind of complex spatial problem where quantum advantage becomes apparent. The positioning of each turbine affects the performance of all others through wake effects, creating a highly interdependent system. Topological quantum computing excels at maintaining these complex relationships in superposition, exploring the full solution space to find globally optimal configurations rather than local maxima. Manufacturing giants like Siemens and BASF are exploring topological quantum machine learning for materials discovery and process optimization. Quantum-enhanced simulations of chemical reactions and material properties enable the development of next-generation catalysts, batteries, and structural materials with precisely tailored characteristics. Industry analysts project that quantum-accelerated materials science could reduce development cycles from decades to years, with profound implications for sustainability and economic competitiveness. Materials science is fundamentally quantum mechanical in nature, making it a natural application for quantum computing. Topological quantum systems can simulate electron behavior in complex molecules and materials, predicting properties that would require prohibitive computational resources on classical computers. This capability accelerates the discovery of materials with specific desired characteristics, from superconductors to lightweight structural components. The rapid advancement of topological quantum AI has raised important ethical and geopolitical questions. Unlike previous quantum computing milestones, which were largely academic, these developments have immediate practical applications that could disrupt industries and shift the balance of technological power. China has responded by announcing a $10 billion initiative explicitly focused on topological quantum computing, while the European Union has incorporated topological qubit research into its quantum flagship program. The United States National Quantum Initiative has redirected significant funding toward topological approaches, reflecting a growing consensus that this technology represents the most promising path to quantum advantage. This international competition reflects the strategic importance of quantum computing as a foundational technology that could determine economic and military advantages in the coming decades. Nations that master topological quantum computing may gain decisive advantages in cryptography, materials science, drug discovery, and artificial intelligence. Privacy advocates have expressed concern about the potential for topological quantum AI to break currently secure encryption protocols. Dr. Michelle Mosca of the Institute for Quantum Computing warns that we may need to accelerate the timeline for implementing post-quantum cryptography by several years in light of these developments. The concentration of topological quantum expertise among a handful of technology giants raises concerns about technological monopolization. Smaller nations and developing economies risk being left behind in what some call the second quantum revolution. International bodies, including the United Nations Office for Disarmament Affairs, have begun discussions on governance frameworks for quantum technologies, with particular attention to dual-use applications in cryptography and artificial intelligence. The security implications extend beyond encryption to include concerns about quantum-enhanced surveillance, data analysis, and autonomous systems. The same capabilities that make topological quantum AI powerful for beneficial applications could potentially be repurposed for privacy invasion or military applications. As topological quantum computing continues its rapid evolution from theoretical curiosity to practical technology, we are witnessing the birth of a new technological paradigm at the intersection of quantum physics and artificial intelligence. The mathematical elegance of topology provides a robust foundation for quantum computing, while quantum-enhanced AI promises to solve previously intractable problems across multiple domains. The coming decade will likely see topological quantum AI transition from specialized research applications to mainstream commercial deployment. Early adopters across industries are already gaining competitive advantages through quantum-accelerated optimization, simulation, and pattern recognition. However, realizing this technology's full potential will require interdisciplinary collaboration among physicists, computer scientists, ethicists, and policymakers. What makes this revolution particularly significant is its foundation in fundamental physics rather than incremental engineering improvements. Topological quantum computing represents a qualitative shift in our approach to computation, harnessing quantum matter's strange and counterintuitive properties to process information in ways that classical computers cannot. As these systems scale from dozens to hundreds and eventually thousands of topological qubits, we may find ourselves entering a new era of artificial intelligence with capabilities we have only begun to imagine. The scaling of topological quantum systems presents unique advantages compared to other quantum computing approaches. Because topological qubits have inherent error protection, they require substantially fewer physical qubits to implement logical operations. This means that a system with a few hundred topological qubits might outperform conventional quantum computers with thousands or even millions of physical qubits. The path to scaling involves challenges in materials science, cryogenic engineering, and quantum control systems, but the fundamental physics suggests a more direct route to quantum advantage than error correction-heavy approaches. As these systems grow in size and capability, they will enable entirely new classes of algorithms that remain theoretical today. The emergence of topological quantum computing represents a fundamental shift in our technological capabilities. By harnessing the strange properties of Majorana zero modes, researchers have created quantum systems with unprecedented stability and coherence. This breakthrough isn't just another incremental step in computing power. It's a paradigm shift that enables entirely new approaches to artificial intelligence, drug discovery, materials science, and optimization problems across industries. As governments and corporations race to develop this technology, we face important questions about access, security, and governance. The mathematical beauty of topology has provided a solution to quantum computing's greatest challenge, opening doors to computational capabilities we've only begun to explore. The marriage of quantum physics and artificial intelligence through topological protection may well define the next technological era, solving problems that have remained intractable throughout human history. As these systems scale to hundreds and thousands of qubits in the coming years, we stand at the threshold of a new computational age with profound implications for science, industry, and society. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.